Hello everybody. Welcome at the second part of a session on tool deterioration, toolware. In this part we are going to focus more on tool deterioration. How do we measure it? How do we assess it? How can it help us, if we manage it well, to improve our production? That's the main subject of today. And as always, of course, I'm not alone here. I have the fun part. I can talk about what I find so intriguing, machining. But of course, some people have to work and make all of this possible. And again, here Olivier and Alesia are my two colleagues helping me with this. If we talk about tool deterioration, toolware, there are a number of things I would like to draw your attention on. This little book, I think, is a must-read. It's on tool deterioration in general. It explains quite a lot from a practical perspective. And also another thing I would strongly advise is this book. This thesis from Rebecca, who last week successfully defended it, and it's her PhD thesis. This book reveals quite a lot of things which were still uncertain. There are some questions left open, of course. That's how it goes with toolware and tool deterioration. But two interesting books to read and to consult. The agenda of today is rather extensive. There are quite a lot of things I want to bring under your attention if we talk about tool deterioration. And perhaps the first one to start with and to position a bit what exactly we are talking about, small batch production. And small batch production, perhaps you remember that last time I called small batch machining production a jungle. It's a jungle, and in that jungle what you see is that machines are standing still. They are supposed to function, to work, to produce workpieces, but they are not. They are standing still. Tools are unfindable or broken. Operators are stressed, frustrated. Workpieces are scrapped because the quality is no good. With other words, it's a jungle. And that jungle is meaning that if you look careful into it, that and I take just an example here. I take the example of that so-called OEE, the overall equipment efficiency, which is something that people managing production, organizing production, are using as a tool to evaluate how efficient machinery is used. And the subject today is not this thing, but if you measure OEE, what you find out is that machines are available for a long time, 24/7. But if you really dive into and you start measuring and you try to measure how much of the real time machines are effectively producing workpieces, it's very little. That means that you have a very expensive piece of equipment, a machine tool, a milling machine, a lathe. And from an efficiency perspective, one could kind of say it's a bad investment. And if you really, next to measuring it, try to figure out what exactly is causing that very low OEE, what you see then, and I think it makes sense, I think it's logical, but anyway, what you see then is that a big number of reasons why machines are not doing what they are supposed to do, producing correctly finished workpieces, is due to the process, is due to the tooling which is used. And we have to be careful here. I don't say, absolutely not, that the tooling which is being used is of bad quality. What I say, on the other hand, is that whatever the quality of the tooling being used in the workshop, how the tools are being used is questionable. Because if you look, and what you see here on the screen is just an example, it's just a typical example, which of course case by case will be different. But if you look really to time losses, the so-called minor stops on a machine tool, in 50% of the cases, and it's depending a little bit if you have a turning or a milling or whatever operation, but 50% of the cases that the machine unplanned is stopped is due to that big thing I refer to as tool deterioration. And you remember last time we said tool deterioration is a phenomenon that indicates that a tool is losing the ability to perform in line with expectations. That's what we call deterioration. We also defined wear. Tool wear is a physical phenomenon, meaning that if two bodies in solid state are in contact with each other, and there are on the contact surfaces there is certain pressure and there are temperatures and there is movement, the two surfaces are going to suffer from that. And that damaging which we see on surfaces is what we call wear. So tool deterioration, tool wear is not exactly the same. In tool deterioration, part of the reason why tools deteriorate is wear. But there are other stuff. See what we talked about in the first session, and we are going to talk a little bit more here also, because it's important to next to wear also recognize what other phenomena lead to deterioration. So if in that small batch production we call a jungle, I call a jungle. If we look to for example machinery, if we use as a measurement, as a metric that OEE, and we dive into and we try to figure out what exactly is causing that OEE losses, we nearly instantly fall on the tool. How a tool is used, how stable a tool is, what type of wear there is, and so on. That leads me it's a bold statement perhaps, but I dare to say, if you master your tool deterioration, if you control your tool deterioration, tool wear, you are working on your manufacturing excellence. And manufacturing excellence, perhaps you remember last time in part 1, we also defined manufacturing excellence. We said manufacturing excellence is running your production in such a way that whatever you want to achieve, you do it better than your competitors. And as such, you create a competitive edge towards customers and you are successful in your business. So suddenly now tool deterioration, tool wear, I link it on success in business. So a statement I would like to do, tool wear, tool deterioration, it's a technical thing. And traditionally we leave it in the hands of technical specialists, but if we are clever, we should lift it to a higher level also, because there are other things in tool deterioration than just a bunch of recipes of what to do if there is a certain wear pattern on a tool. Now, to do that, to make a start, there is something I refer to as global tool deterioration analysis. Now, what is global tool deterioration analysis? Let me start first with the word global, because that could lead to confusion. Global means total. And I draw your attention here on the fact that we call it tool deterioration analysis and not tool wear analysis. Of course, tool wear analysis is part of it. If I want to analyze tooling, if I want to analyze deterioration effects on tooling, of course, a big part of it is the actual wear. And there we have all kinds of methods and systems to measure wear, to observe wear, to quantify wear, and to learn from it. But that's not enough, because tools deteriorate not only due to wear, but also due to what could be questionable choices which are made in the life cycle of a tool. Ranging from selecting a tool to purchasing a tool and so on. Sometimes, as I said, that tools lose their ability to function well is not really the quality of the tool, but it's the tool itself, the selection of it is perhaps not in line with the application we have for the tool. And also here there are all kinds of things we have at our disposal for analyzing and for synthesizing, coming to certain conclusions. Tool selection strategy, as I said, is so important. That's why most of the time we put it also even in a separate chapter. Tool selection is part of the total life cycle, of course, but on the other hand, it's so important that it's worthwhile putting it in a separate thing also and dive really into the selection procedure for tools and cutting conditions. I come back to that later. Machining expertise, the people effect. Personally, in all the years I worked in machining, I saw possibilities from equipment becoming bigger and bigger, but on the other hand, I also saw more and more an underestimation of the importance of the human factor, because in the end, the human brain is adding intelligence to the whole system, or could do it if the expertise is correct. So part of a global tool deterioration analysis is daring to analyze if the people using the tools really know what they are doing. I put it a bit boldly here, but it is that. Because a tool can have the best quality in the world and the selection procedure can be done in the best possible conditions, but if the person having to work with the tool, manipulate the tool, have no idea how to do that, again, there is that old saying, a cutting tool is only as good as the one using it. It's very simple, and to make the picture complete, because machining there are three legs always. You have the tool, you have the operator, the engineer working with it, and of course you have the machine tool. That's the third part. And those three must be in balance. So if we talk about a global tool deterioration analysis, of course we look at the tool, the red part on top, the wear phenomena. We look around the tool about how do we select tools, how do we handle tools in the total life cycle. It's the second layer, and the third layer is around the machining process, around the tooling, actually doing the cutting. How is it with the people, offering intelligence to the whole system, and how is the machine tool being used, and what limitations do we have from a machine tool, or what possibilities do we have from a machine tool that perhaps we don't use fully or exploit fully. Mapping the life cycle of a cutting tool. If you look from a cutting tool in the most generic way, there are 6 stages, one could say. The life of a cutting tool starts by that it is being selected to do a certain job. Once it's selected to do a certain job, it's being bought, it's being purchased. Now, purchasing can mean external. When the tool is not present in the organization, it needs to be brought in. It can also be internal. With other words, purchasing for me is the tool must be available after it has been selected. Third stage is the tool is kept in inventory, ready to function. Tool inventory is the third phase, one could say. At a certain moment in time, it's decided that it's time to start working. Then the tool is prepared for the job. Tool preparation means, for those a bit familiar with those things, that a tool assembly has to be created. A tool holding tool, a tool holder, perhaps inserts in it, or a solid carbide. The tool has to be set, the dimensions needs to be measured, all that type of stuff. That's what we call tool preparation. The fifth phase, the tool is actually machining, doing the job for which it has been selected in the first place in phase 1. And after the job is done, the tool is put in the 6th stage where aftercare is done. Now, aftercare for me is, it starts with an evaluation. In which condition is the tool? And basically the tool is still capable of being used for a next job. And then it goes back in phase 2 or phase 3 in this schedule. Or somebody decides this tool reached end of lifetime, and then the tool needs to be removed from the cycle. So in a very generic way, these 6 steps are the total tool cycle or the life cycle of a tool. Now, if you dive in a little bit more in depth in that, it's not so easy. Because for each stage, there are kind of a million questions that needs to be answered. And that makes this thing a bit difficult. It's not only for those looking into this aspect, it's not only to understand the full cycle, it's not only to understand where a certain tool in this cycle is, but it's also about all the questions around it. And to make sure that everything goes correctly, let me give you an example. You have post-machining, tool in the aftercare. When a tool arrives in that stage, the first and utmost important question is, what is the condition of the tool coming back? Is the tool still usable? Is the tool not usable? Can the tool be recovered? Does it need regrinding? Whatever. All those things. First phase in the last stage. And then a very simple question: who is doing that? Who is asking that question? Who is making that analysis? Because the outcome of it is very important. Because if that person or if that system fails and a tool is thrown away while it was still capable of doing something, that's a waste of money. On the other hand, if the tool is kept while basically it's not capable anymore to work in a safe way, that creates quite a lot of stress in this system, because there you create an insecurity, and the next time the tool is going to be used could create all kinds of problems. So the questions here, the total mapping, finding all the answers on all the questions is what we talk about when we say mapping of a tool life cycle. Part of it, the first stage in a life cycle, is selection. Now, tool selection, I again start with a rather bold statement. I claim it starts with company management and it ends with company management. Because, and I give here 2 examples, and I see it so often. It's like in a company, tools are needed, and then it's like buying a new car. And somebody goes to a garage and says, I need a new car. And after a while, they end up in discussing what type of rubber on the tires of a car. In the basic purchasing situation, buying a car, that's a bit, I think that's strange. A second example is in the buying process of a car, everybody's talking about the consumption, but once the car is being used, nobody does any follow-up on the consumption anymore. What I try to say here is that in a purchasing process, in a decision process, the details, the geometry, the carbide grade, the cutting condition, all of that details come in the end, not in the beginning. In the beginning, it's a management decision. And it's a management decision, and one could say there are 5 steps. Step 1, what are the company KPIs? What does the company stand for? Does the company wants to deliver high quality work, or is productivity the key thing, or is cost efficiency? What are the company KPIs? Secondly, what are the application KPIs for the tool? And we should make sure that the company KPIs, the overall targets, and the targets, the generic targets we put on a cutting tool, they are in line. They reinforce each other. If you say, I want to have high productivity, and on the other hand, you select a tool which is the cheapest possible, could work, but most probably won't. If you go for productivity, you need, from a tool perspective, performance. You understand? These two needs to be in line. Once that's settled, then you can start talking about the technical details. What are the features the tool must possess to be able to fulfill the demands? The carbide grade, the geometry, the dimensions, all that type of details. Together with it, how are we going to use the tool? With other words, machining strategy, cutting conditions, cutting data, and so on. And here it's a bit tricky because it's something. Sometimes when I'm nasty, I ask the question to people and I say, what comes first, the chicken or the egg? What I mean with this is what comes first. You first select a tool, cutting tool, and then you go for strategy and cutting data, or you first define what strategy would be most useful and what cutting data you would like to use, and then you try to find a tool that makes that possible. And this is a question I think so far it can only be solved by numerical approaches. But it's an intriguing question. What comes first, the tool or the cutting strategy? And which one defines which one? Now, if we look to company KPIs, very typical, it's productivity, economy, quality or versatility, flexibility. That are the four big families. If you look to the generic KPIs for tools, it's about reliability and performance, the ability to perform at high level in a reliable way. It's economy, cost per cutting edge or per part or per whatever you want to define. It's about precise and sustainable cutting edges. That's a third KPI for a cutting tool. And the fourth KPI, a bit opposite to the first one, is to which extent is a tool capable of doing more than one type of application. Versatile, flexible. Now you have 4 company KPIs and you have 4 tooling KPIs, generic tooling KPIs. The first 2 steps in tool selection is combine these two. What are your company KPIs and what are the KPIs from the tool we need to focus on to support the company KPI? Once that is done, you can give the whole thing to a technical specialist and tell him, figure out the details now. Figure out the features, figure out the cutting conditions, the strategy and so on to make sure that the 2 overall demands are fixed. As I say, it seems easy. I can tell you in reality, it's a battle. Because, and I hope I don't offend anybody, but I sometimes have a feeling that company management do not really appreciate the difficulties of tooling. They say, yeah, the tool must be high performing. Yeah, but what do you mean with high performing? How do you define high performing? Because if you ask the technician, the guy behind me here, and you tell him high performing, what do you want? He will say high cutting speed. That's his definition. And if the guy on my other side says, no, it's about cost, the technician will say, then it's about tool life. Now, that is very simple, in most cases, very wrong thinking. So it's a bit of a difficult exercise. And if you work with these things, you know, in 5 seconds you can see how far a company is in this. You see behind me 2 photos. Well, the photo here with thumbs down, if you open a cabinet and it looks like that, then you know the battle is ongoing. And sometimes the technician wins and sometimes the manager wins, and in the end it's one big mess. If, however, the 2 come together and can formulate a common target, then it more or less looks like the other photo with the thumbs up. So a very simple observation gives you an indication how much diplomacy you are going to need handling this situation in a workshop, in a company. Mapping machining expertise. If you look to people in machining, it could be an operator, it can be an engineer, it can be an expert, whatever, people working with machining processes. What do they need to be called expert? Well, first of all, they need knowledge. Knowledge for me is insight, and insight gives a very important possibility to predict. And I would like to introduce the word predict, predictive, preventative, or the words preventative into machining. Because in my eyes, machining is still too much a situation where people kind of a down attitude. Yeah, we don't know, we will see. We try and we will see. Now, I don't think that should be allowed in these modern times anymore. Insight gives us the possibility to foresee, to perhaps not 100%, but at least to have an idea. If I do this, this, and this, that should happen. That's the power of knowledge. Of course, knowledge without skills serves no purpose, because you have to be able to put knowledge in practice to make it work. This is a bit the why, what, and how, you know. Knowledge answers the why question, and skills tells you what to do and how to do it to make it work. Of course, you need equipment to do the job, and a machinist must be able to handle that equipment. Because you remember one session we talked about cutting forces, and I said, if you measure cutting forces, yeah, that's good. But you need measuring equipment for that, and a machining expert needs to be able to work with that equipment if supposing he wants to do something with cutting forces. So equipment, what equipment is needed, how does it work? Here there's also a message from management. You can expect a lot from a machining expert, but an important task for management is to make the equipment available for the guy to do his job. And mindset. Mindset is something that you know, personally, I also rather late in my career started to appreciate the value of mindset. I thought if you have knowledge, and if you have skills, and if you have the equipment you need, everybody wants to do a big job, a great job, but that's not always true, and that's a bit the human aspect, you know, the mindset of people. Sometimes I take it on myself. I have 40 years experience. Yeah, that experience I can use, if I want to use it, I can use it to destroy a milling cutter in 10 seconds, huh? If that is what I want to do. That's mindset. It can be the best milling cutter in the world, you know. But yeah. Is there an easy way to have an idea what the situation is in a workshop, and a trick I use sometimes, and there is a name for it. I didn't invent it. It's something. It's one of those metrics that people managing production sometimes work with. It's called the mean time to restart. The mean time to restart is where we measure. Imagine you have a machining process. Everything is running smoothly, and suddenly something happens, and the operation stops. See the photo here, the tool is broken. The operation stops, and kind in a negative way, now the machine is standing still and the clock starts ticking. The machine is standing still, is not being productive. Remember the OEE. This is the start of a so-called minor stop. The first thing somebody must do then, the operator or the expert or the foreman, whoever in the organization we talk about, is diagnose the problem. What happened? Why did it happen? And what should we do and how should we do it to repair the situation? That's the first thing to do. What happened? Why did this happen? What do I need to do to correct this and continue production? And how do I do it? Then the second part comes, the actual repair. I repair the situation. And then at one point in time, everything is ready and the machinery starts again and the clock stops ticking. In between, you have what we call the mean time to restart, because this is, of course, how long it takes is depending on the problem. As some problems can take a long time, other problems are solved in 5 seconds, but it's just to have an idea. And you know, when I'm in a workshop doing projects, I do it so often, just seeing, and without mentioning it, but just seeing, wait until I see or hear an accident and then observe what happens now. And you know what I'm talking about here. If you can make that time shorter, it influences your OEE because the percentage of minor stops is going to be reduced. And that means all of that is time that becomes available for production. So if you can make this time short, you have an increased availability, reliability, you have happier customers because you don't have to call them, ooh, an accident happened and production is delayed. You save money, of course, you increase your productivity, only positive things. But to make the time short, to have that quick reaction, accident, what happened, what do? I do it and I start again. You need skilled people, knowledgeable people, because if the people are standing there and they say, I don't know, no idea, very strange. Yeah, while standing there in doubt, the clock is ticking. Huh? So the level of knowledge, the level of skills available in a workshop, in a company, impacts directly this metric. And I use it in a different way. If this metric is minor, if the values are low, that's for me an indication that the people being confronted with this have knowledge, have skills, have insight. It's again a very simple observation. To start with, of course, when you dive in, then it's getting a bit more complex, but just to have an idea. And then finally we come to the toolware analysis, what you perhaps have been waiting for. Now, if you look to cutting tools, I dare to say that every used cutting edge is kind of a bit or a byte of data. But on the other hand, if you look to every cutting edge is unique. So you have an enormous amount of data after a while, all those used cutting edges. But how can we be selective? Which ones are valuable for us? Which ones are relevant for the situation? That is the thing we are confronted with now. So the data are there, kind of. But how do we handle the data? How do we find the really relevant things in between all the noise, kind of? That is the challenge we have here. Now, how to observe toolware? I still believe, but I suppose that's my experience, that's my time, that the human eye with a little magnifier is what we need, or a digital equivalent of that, and a simple measuring thing. Because what I want to know, if I look to every cutting edge, is what is the wear pattern? That's why I need this. And the other thing I need to know is how big is it? And that's why I need this. Now, again, that's easy said here. Experience is very important for this. Expertise is because you will have to answer, if you do that observation, there are quite a lot of questions you need to answer. First of all, there are questions to start with. before you start evaluating your data, you have to ask yourself the questions in the situation you are, in the workshop you are, the applications you have at hand. What is the preferred wear? What is common wear? What is not common wear? What is controllable wear in this situation? What is predictable wear? Do you have all the information needed? Is the sample you have representative? For the situation. Who decides on tool indexing? Who decided this cutting edge is used and goes to the bin? What criteria did that person use to make that decision? And so on and so forth. So it's not only looking at tools, it's asking questions. And in a first thing, in a first step, what we want to do and a direct advantage is if you watch all these things, what you will see is that a number of cutting edges have so-called preferred wear. What is preferred wear? And I again refer to part one. Preferred wear is controllable wear, is where you can influence. So if you are unhappy with it, that you have a number of things you can do to work with to improve. I know some people have problems with preferred wear. Wear is never preferred, yeah, but wear is a physical reality. Wear will always be on cutting edges, but I want wear I can control, I can predict, I can handle. That's preferred wear. Other wear patterns I do not want because they are unpredictable, I can't control them, I can't influence them. And what you see in a lot of cases when you start to work with this, that the unwanted wear is the majority. And the first direct thing I want to do with tool wear analysis is to change that picture, to give advice that the preferred wear pattern become the main ones, the major ones, and that unwanted wear is minor. If you manage already that, you see that you have two big things already done. One, you minimize tool consumption, that's a direct saving. And secondly, you increase the reliability of the operation. And that you will notice afterwards in that your quality is more consistent, that you respect more time promises you made to customers, that your costs are better under control, and so on. That's the first direct thing. As I say it here, tool wear analysis, learning how to do it for me is to a big extent still today hands-on job. By doing a lot of them, you gain expertise. And real life cases in this respect is everybody who wants to dive in, I would say start by doing it. And the first ones will be doubtful, but when doing, you will learn and you gain the expertise. Watching cutting edges, a second series of questions come. The first was, what would I like to see in a given situation? That's the pre-investigation. In this situation with these applications, the ideal world would be if I see this and this and this and this. Then you make your observations, then come the next series of questions about what do I see? And that is questions is in sense of, is it aging wear that I see, or is it sudden breakage? Do I see singular wear patterns? Do I see multiple wear patterns? What's the primary wear? What's the secondary wear? Where is the wear? What's the position of the wear? How big is the wear? What's the frequency of certain patterns? And so on. A typical, observing things. If you observe later on in the synthesis of the whole exercise, you need benchmarks. And benchmarks is reality. Because I always take an example, broken cutting edges. If you ask people broken cutting edges, people say, we should not have broken cutting edges. Of course not. But the reality is there will be broken cutting edges. That's how it goes in machining. But we should try to work with a benchmark. In similar situations where things were well under control, how many broken edges did I see? I take that as a benchmark and then I compare with the situation I'm working in and I see where am I with this. Is it in line with expectations, or is it better, or is it worse? Preferred wear, common wear, all that type of things, that refers to the application. That's the knowledge part, that's the insight. You should have the knowledge if you machine titanium, that you know that when you machine titanium, these are the typical wear patterns I will see. And if that is what you see, fine. If you see different, then you have an issue. And this is more complex than the old school flank wear. Because too many people still say flank wear is what we want to see, which is very perfect in big batch production of steel products. Small batch of titanium, you see quite a lot of other stuff. So be flexible there. What is controllable? What is predictable? How is the variability of what you see? Do you see it just once, or do you see it regular appearing on cutting edges? The size, measure and classify. Here it's a bit of a statistic exercise. How many of this, how many of this, how many of that? Involve other signals you have from operators. Ask the operator, find out who decides on when changing a cutting edge, and ask that person, what are his criteria? What is he using as criteria to take a decision? A very important thing here also is that you should have an idea after how many minutes cutting a cutting edge was classified as has to be replaced. That's a bit of a tricky one, however, I have to admit. And then you put everything together, you create kind of a statistical picture. So it's about finding out of your sample of used cutting edges, how much age-based wear, how much sudden impact failure, broken cutting edges, how many unused tools, because if you start to analyze, you find out that a number of cutting edges are in the bin to be recycled and have never ever made one ship. A very important question then is why? Size and position of the wear, variability in singular and multiple wear patterns, deviation. If you see quite an example, a lot of flank wear anyway, but is it all kind of the same, or is some very small and some very big, and is it very widely spread? Variation in types of cutting edges. Did you evaluate only one type of cutting edge, a triangular insert, or was it a big variation? Because wear on cutting edges depends also on the type of cutting edge you use. Utilization ratio. What part of the cutting edge has been used? Ship formation. It's always interesting if you do a wear analysis also to have a look at the ship conveyor, the ship container. See what type of ships you find, and how stable are the processes. Do you observe instability? Do you observe vibrations? Because those will create very specific wear patterns. And then you come to a synthesis. And okay, based on all your observations, compared to benchmarks, so you have your overview, you have details, you have directly connected to that direct savings possible, if applicable. And based on that, in the synthesis phase, you can come up with proposals to improve. And remember, what we are after here is not only technically a better choice, but is also higher manufacturing excellence. That the overall picture of all all elements in the operation improve. Better OEE, more consistent quality, less frustrated operator. It's a full picture we are after here. It will help us to evaluate a bit more in depth how tools were selected, because based on what we see, we can take certain decisions about, we should put more emphasis on certain types of cutting materials or geometries. It's a possibility. We can find out the operators, do they need schooling? Because very often they are the ones, I talk about small batch production now, they are the one who take the decision to change the tools. Yeah, is that done in the best possible way? In every company, and very often neglected, there's what I call tribal expertise. Because every company has kind of, we are specialized in whatever machining. And over time, people learn the exceptions to the general rules in their situation to appreciate them. And it's important that that is kept for the future. Also asking questions about how tools are selected. From day one, kind of. Are the methods used? Are the criteria used? Yeah, in line with reality. Equipment, is the equipment there to work with all this? And make sure, because it's a small thing, but very often when I do seminars, I ask people, do you know how much a tool costs? And it's incredible what answers you get. Some people think it's gold. At least for the price they mention. And other people think it's chewing gum for the price they mention. So it's interesting and important that people have a real feeling for what we talk about. It's about helping people also. When they have to take decisions, this tool should be used, yes, no. Give them some guidelines, give them some instructions. And working in a continuous way. I mean, there are quite a lot of workflows you can have in a company, working with tools and working with tool performance. And again, it's not about technical stuff only. I have in mind also my manufacturing excellence. Make wear monitoring a more structural thing in the company. Don't leave it at random. Yeah, the operator should decide when to change an insert. Yeah, based on what? Make some structural stuff there. Make sure you have expertise in-house. Don't trust always on external people. Make sure, especially for your tribal knowledge, the knowledge very typical for the company, make sure that you have people capable of working with that, handling with that. And based on that, you can create improvement projects. Make sure that you have a well-structured and documented life cycle management system for cutting tools. You all know it, that people know the tool is there, but nobody finds it. And when they find it, they find out that it's not capable of being used, because or it's completely used out, or first some things needs to be done. And that should not happen in a company. Make sure people have all the education, the training they need to do a good job. The tribal knowledge, as I already mentioned, is every company knows about it. Every company knows how important it is. Every company knows it's in the head of the experienced people. And then suddenly the experienced people retire and the knowledge is gone. And I think that's especially in these digital ages, that knowledge should somewhere be kept and saved. And of course, if you talk about tool monitoring, tool wear monitoring, with all the digital possibilities we have today, there's quite a lot of stuff we could do there, we could create there. Indexing strategies. So if you have the expertise, if you have a system to have representative samples of used tools, if you have the knowledge on your side, if you possess the knowledge, if you use these three And if you look to your used cutting tools in a systematic manner, and if you connect that to your company KPIs, whatever they are, based on that, you have the 3 basic building stones. You have a systemized method for evaluating your tooling, and you know what you want to achieve with your company. You know what you are after when we go for manufacturing excellence. That should help you in things which are today too much left at random. You know, tool indexing, if you ask people, if I ask people, when do you index your cutting tools? The answer is when it's needed for. And then I say, okay, when is it needed for? I look at the cutting edge and based on what I see, I decide it's needed for or not. And then I ask, when do you do that? And they say, at random, now and then, in between 2 work pieces. Now, that should not be like that. The word preventative, the word predictive is valuable. You know, in machining, if you really do an in-depth analysis, the tool indexing is the only thing left that so far is not really automated and still left at random in a workshop. Go for more preventative, more predictive approaches, even for tool indexing. And make sure the people having to take the decisions, that they have the knowledge, they have the skills, they have the equipment, and create a structure in it. Tool deterioration, if you control it, if you manage it, if you're on top of it, you're on top of productivity. If you look in productivity in machining of small batch production mainly, and if you control tool deterioration, you have it. And a global tool deterioration analysis, the overall picture as I showed you, and it doesn't need to be a very long time taking exercise. I told you there are some simple observations you can use to have directly already a good idea. Can be a very interesting first step if you want to improve. What I want to bring under your attention is a proactive attitude. Don't wait and answer, we don't know, we see, we check now and then, we do when needed. Proactive. Learn from your tools, learn from the observations you make, and use those to create a structure that people in the future can use in a proactive way. If, then. That's where we want to come with this. And if one thing I thought I have to add this, because very often when you start talking about these things, what especially managers, they say, yeah, but you know, if I start to talk about structured approaches for tool deterioration management and stuff, my operators don't like that. Because, you know, operators, very strange people, but I do not agree with that. Because machining people are very proud people, and you know, if you really talk with them, they feel themselves a little bit embarrassed that if you bring up the toolware thing, that they say, If you approach this, you know, in the end, a very nasty activity in a workshop is the so-called finger pointing. A tool breaks and everybody focus on finger pointing. Why did the tool break? Because him or she or whatever. And if you have a more structured approach, that disappears and the finger pointing disappears. And believe me, you have the operators on your side. It's that human thing I felt important. I want to mention this. If you said all this seems interesting, how can I start this? Well, first make sure you have knowledge, and if the knowledge is not there, participate in a seminar, in a masterclass on tool deterioration or whatever, make sure you also possess the knowledge, your people possess the knowledge. Look at the tool, the second thing. People is one thing, the use tools is another thing. Do a tool deterioration analysis, or if you think it's too vast for you, do a tool wear analysis to start with, and start learning what your situation is. It's next to people, it's the second thing, and the third thing, and it's all a bit based on lean manufacturing or on QRM manufacturing. It's about go out in a workshop and observe the process. As I said, mean time to repair. How long is the machine standing still when a tool breaks? How long is the machine standing still when ships are too long? How long is the machine standing still if whatever? Read your process. Analyze your process. Read your people. Ask people. So the 3 first steps, make sure you have the knowledge, and if you have doubts, there are enough possibilities to gain knowledge. Books. The books are available if you prefer reading. People. And use tools. Your 3 cornerstones. I see I overstepped a little bit the time. There's not so much time left for questions, but anyway, we have some minutes left. For those who want a copy of this presentation, of course, is available. Just send me an email or put something in comments, and I make sure you have a copy of the presentation if that is what you want. If you want to have information on these books, idem dito. Send me a message and I send you all the information around all the technical literature which is available. Also for your information, on behalf of Rebecca, for those interested, I can offer you this, at least in a digital version, and I strongly recommend it. It's one of the, from a professional perspective, one of the most interesting things I read the last years is perhaps a bit exaggerated, but the last time. Really interesting stuff. Any other question? Of course. Just let me know, and if I can help you, with pleasure. And then let's see now if there are questions. I have to keep my eyes on the time. Where can I find copies from the book? Yeah, I already just mentioned that. Another question, what is OEE? Yeah, OEE, it's an abbreviation. It stands for Overall Equipment Efficiency. In machining production, we use it to measure the time spending on a machine tool. A machine tool is available 24/7, in theory. But in the end, if you measure actually how the machine is being used, you find out that the actual time the machine is producing work pieces which are correct is a lot less. And in between, theory 24/7, reality it's being used, I don't know, 20% of the time really. In between you have 80% loss. That's the measuring part. The real interesting thing is figuring out what is causing that loss and what can we do to minimize that loss. So that is what we do with OEE. By the way, one of the team members here, Olivier, he's an expert in that, so you can send him also messages if you want to know more about OEE. Then there's the question. Yeah, I was thinking that was going to come. You mentioned that deciding on the tool, machining strategy, and cutting data, it's chicken egg thinking. But what is best? To be honest, that's a question I cannot answer in 2 minutes. I try, but it's a very generic answer. in most cases, you should look for your operation in such a way that you remove as much chips as possible in the shortest possible time with a cutting data combination of big depths of cuts and feeds and moderate cutting speeds. All of that within what is possible for the machine tool you use. And then next comes, if you do that, and you want to have an correct tool life, and that's the economic side, then you should select a cutting tool that allows you to do that. To select that type of cutting conditions on a certain machine and workpiece, and gives you the appropriate tool life to have the economic side of your operation correct, and then you need a tool with the features making that possible. Now, I do know it's a very generic answer, but in general, one could mention like that. The time is up, but anyway. Can you please tell whether tool deterioration... okay. Yes, there is a very clear relation between tool deterioration and types of chips. I would perhaps it's better to say there is a very clear relation between tool wear and type of chips. If you have continuous chips, ribbon chips, the process is working more stable. And that means that you have more traditional wear patterns. If you have shorter chips, irregular shaped chips, you will have issues with so-called micro vibrations. And micro vibrations are going to create more the type of wear which is typical for failure, you know, little cracks and shipping and so on. So the type of chips is influencing the type of wear you are going to see. And some of the wear is what we like. The progressive type flank wear is what we like because we can do stuff with that. While the other type, the shipping type, is more stochastic. There, it's not so obvious altogether. Then there is a question about coolants and cooling oil. Will they affect how the tools work? Of course, and that is a subject on its own. Of course, there is a relation between that, and yeah, we should spend a session on that because I have had that question so often now. That really it deserves to put things a bit in a structured way together. That question is answered a bit. Yeah, sorry because I have to keep the time also here that I don't dive in too much in that. One last question. We are already over time. What is proactive tool indexing? The way I define it is proactive tool indexing is deciding to index the tool proactively, meaning the moment you decide, you know it's in 90% of the case the correct time to do it. And not each time again, the stop, evaluate, yes, no, perhaps, and continue anyway. Proactive is, I know at this moment or after that workpiece, it will be time to index the tools. That's proactive tool indexing. And here, yeah, we are already after 5 o'clock, so I want to stop here. The other questions I'll handle later on in the chat related to this event. I hope session 1 a month ago and this session, the two form one, that it makes sense. We talked about small batch production is a not obvious type of production. I call it a jungle, perhaps a bit exaggerated, but anyway. That leads to quite a lot of things that people that manage production do not like. But yeah. What we talked about is how is the performance of a tool, the status in which a tool is, relates to that phenomenon. And we learned that tool deterioration and tool wear are two important things there. Tool wear is a physical thing. tools wear out. Tool deterioration is a condition status. A tool is in a condition, is in a status that it's capable of performing in line with expectations or not. My statement was, if you control tool deterioration in a better way, if you manage your tool wear in a good way, in a proactive way, you can contribute with that quite a lot, and I use the example of OEE, but it's just an example, quite a lot to improve your manufacturing excellence. That was the core of my presentation. 2 times 45 minutes, very short, but anyway, I hope I made a consistent picture for you. And as I said, if you have further questions, please do not hesitate to contact me. For the time being, you know, here in Europe, it's that time of the year again. That summer holidays are around the corner, so we kind of stop here for the summer holidays. I hope you all enjoy them. The people in Europe at least enjoy their holidays. I hope to see you back in September after the holidays somehow, that we can continue this adventure together, because there are quite a lot of things we still should have a talk about. Noticeable cooling during machining is a very typical example. Thank you very much. I hope it was interesting. Enjoy the holidays for the European people, and hope to see you back after the holiday period. Thank you.